lots of things to talk about on the PowerPoint for today, starting off with a review of Ohm's law and the basic terminology that you want to bring to the forefront of your mind is resistance, the concepts of resistance, the concept of current, and the concept of voltage. Each one of these is spelled out in previous documentation that the concept of voltage has what units? The units of voltage are volts. What is the symbol for volts? A capital V. The concept of current is represented by what symbol? Current is represented by the capital letter I. What are the units of current? The units of current are amperes or amps. And what is the symbol for amps? That would be, sorry for this lamp. The symbol for amps is a capital A. What is the symbol for resistance? The symbol for resistance is capital R. What are the units of resistance? Ohms. And what is the symbol for ohms? Is the Greek letter omega that looks like the horseshoe. And so what do each of these concepts represent? Voltage is the push, the pressure behind moving electricity in the circuit. Current is the actual flow of the electrons within the circuit, or flow of the holes if we're talking about conventional current. Resistance is how much constriction we have on that pipe that allows a certain amount of current to flow. So if I have lots of resistance, think about this. It's like the pedals of a bicycle. When you pedal your bicycle, one foot goes up, the other foot goes down. One foot goes up, the other foot goes down. So if resistance goes up, then current must go down. If resistance goes down, current goes up. So they behave opposite of each other, inverses of each other. So remember, as resistance goes up, current must come down. If resistance comes down, then current must go up. That is a quick reminder of what we discussed last week. And then we were given Ohm's law formulas, and I've kind of expanded these here. In some instances, the circles, the formulas are shown in the form of circles. Some instances they're shown in the form of triangles. It doesn't matter which geometric shape is used, the mathematical relationships between the quantities in the circle are absolute. That's why it's called a law. It's not his hypothesis, it's not a theory, it is a law, it's absolute. So let's take a look at this very first circle. The very first circle is, thank you for all of you chatting in the background, trying to get our lost souls connected. See that? So if you take a look at the very first circle, what I've indicated to you before was the horizontal line of that circle represents a math function known as division. The vertical line here represents a math function known as multiplication. So here is an example. If you take a look at these triangles at the lower portion of this frame, you see V is circled. If we are looking for voltage, you cover up the V with your thumb, and what's left is a I on this side, an R on this side, and remember the vertical line represents multiplication, which is shown in this formula here. V is equal to I times R. In the next triangle, the circle is around the red ring around the capital letter I. So we're looking for current. If we're looking for current, I goes on one side of the equation. What's left on the other side of the equation? Well, if you cover up the I in your circle, what you have left is a V over R, and that's what's shown in this formula. I is equal to V divided by R. In the last triangle, the R has a circle around it, which means we're looking for resistance. And if we want to calculate for resistance, R is equal to what's left, V over I. So from one circle formula, one triangle formula, you can derive 3 different equations. All you need are 2 quantities out of 3 in order to calculate the remaining quantity. Notice also at the top of this frame is I happen to have in the 2 circles on the left side, the first circle says V equals I times R, but take a look at the second circle. The second circle says E is equal to I times R. what is this thing about V and E? It turns out that V and E both represent voltage. And you'll find in certain textbooks, some authors will use V for voltage, and some authors in the same circle formulas will use E. And E stands for electromotive force, which you should recall as being an alternate definition for voltage. There were three definitions for voltage: the pressure to move electricity through a circuit, electromotive force, as well as the difference of charge between 2 points, or the difference of potential between 2 points. So E and V are used interchangeably for voltage. And yeah, the horizontal line represents division, vertical line represents multiplication. Any questions on this slide? Yes, please. Go ahead, unmute your microphone, Kirsten.
Okay. Can we use epsilon instead of E so that we don't get confused with electric field?
Can you use epsilon? Better to do a capital E, and I will very seldom use capital E. We will, as a convention for our class, maintain voltage symbol as capital V. I show this to you only so that you have a reference of when you look at literature of other sources, sometimes that literature will have a capital E. Don't be thrown off on it, but we will not use capital E. We just want to recognize if we see it, it's an alternative representation for capital V for voltage, okay? Yeah, better stay away from epsilon in this particular case. All right, good question. Any other questions before I move on to the next slide?
Yeah.
Yeah. Cool. All right, sorry about that, everybody. Seldom does the system crash quite that robustly. All right. So, like I say, with the calculator between your ears that mom and dad graced you with, you could do this in your head. So, given a series circuit, I have a voltage source, I have a resistor. If you're given 2 out of 3 quantities, you can calculate the third quantity. So, in the first bullet point, it says if R in the circuit above, R for resistance, is equal to 4 ohms, and I is equal to 3 amps, then voltage is equal to V. Well, find of the 3 triangles, which triangle shows a formula V? The very first one. V is equal to what? I times R. And is that shown here in this part of the slide? I times R. The I is 3 amps. The R is 4 ohms. So 3 times 4 will give you how many volts, my friends? 12 volts. That you should be able to do with mama's calculator, yeah? Next, if I say that the voltage source is 10 volts, and I give you that the resistance is 2 ohms, we're now looking for current. Which of the 3 triangles shows a current formula? The middle one. I is equal to what? The V divided by the R. I have a V divided by R according to the second line, and the V is 10 volts divided by 2 ohms. What's 10 divided by 2? Works out to be 5 amps. Now, the third line. If the voltage above is 15 volts and the current is given as 3 amps, I'm now looking for R. So if you look for R, R is in the third triangle, and R is equal to V over I. I specify that formula here. That's 15 volts divided by 3 amps. 15 divided by 3 gives you how many ohms? 5 ohms. Does everybody get a sense how to apply the Ohm's law formulas, whether they come in circles or whether they come in triangles? As long as you have 2 quantities, you can calculate a third quantity. Any questions on this slide? Next one, Watt's law. Watt, James Watt, a British physicist, had a contribution of these 3 circle formulas to give to us 3 different ways of calculating power. Don't let that throw you. We're really only going to use the first circle for most everything we're going to do for the next week or so. But they all will apply and they all will calculate the same amount of power as long as the parameters of the circuit are the same. So, and what I wrote down here, just like with Ohm's law, with Watt's law, as long as you have 2 quantities, you can calculate that third quantity, okay? So let's take a look at the very first bullet point. It says, if I is current, if I is equal to 2 amps and V is equal to 4 volts, then you're looking for P. Which circle has a P, a V, and an I? So you're given an I, you're given a V, and you're looking for P. So PIV would be the first circle. And if you put your thumb over the P, what's left? P is equal to I times R. And here we happen to have 2 amps times 4 volts. 2 amps times 4, 2 times 4 gives you how many watts? 8 watts. And here's where you've got to keep in mind your engineering terms, your electrical terms. What are the symbols for the concepts and what are the symbols for the units? The units of power is measured in watts, and the symbol for watts is a capital W. Hence, at the end of this line, the first bullet point, I have 8W, 8 watts. The second bullet point says, if the current is 2 amps, and now the R is 2 ohms, I have an I for current, I have an R for resistance, I'm looking for P. Which circle has a P, I, and an R? That would be the second formula. So if I'm looking for P, I cover up the P with my thumb. What's left? I squared times R, which is what I wrote down here for you. I squared times R, which is equal to 2 amps squared times 2 ohms. What's 2 squared? 4. What's 4 times 2 ohms? 8 watts. Interesting. Same power, calculated using a different formula circle because the parameters of the circuit are the same. Take a look at the third bullet point. The third bullet point says, if you're given a voltage source of 4 volts and you're given a resistance of 2 ohms, so you have a voltage, which is a V, you have a resistance, which is an R, and you're calculating for power. Which circle has the V, an R, and a P? Would be the last circle. The last circle says V squared is equal to P times R. Well, I'm looking for P. If I'm looking for P, I cover up the P. What's left? V squared over R, which is shown here. And the V in this case is 4 volts, and I'm going to square that. So what's 4 squared? 16. Divide by 2 ohms. What's 16 divided by 2? 8. I get 8 watts here. Again, 8 watts. So what I've proven to you is as long as the quantities around this circuit are consistent, you can use any of the 3 Watt's law circles and you will arrive at the same amount of wattage. Okay? And the formulas are often used to double check each other. But like I say, don't be intimidated. Most of the time, you and I are going to be using the first power circle formula, P equals I times V. Any questions on this particular slide? Okay, this next one will blow your mind. Ta-da! This is sometimes shown in your textbook and literature. And I will say this, one thing I didn't get a chance to talk about last time was, you can see, I'm going to depart from this for just a moment. Okay, does everybody see what I'm holding? I'm holding up a composition book. And a composition book, in this particular case, this one happens to be with graph rule. So it's got nice squares inside for graph. And so what I offer to the students, and this was citing syllabus as one of the things that you needed to get. It doesn't have to be a composition book like this that is bound. It could be spiral. It could be hardbound. It could, instead of paperback bound. And it doesn't have to be graph. It could be college rule, but you'll find using the graph version is a lot better for you. And that is this. Whatever you handwrite into this book during the course of the normal semester, when we're not doing this completely online, I encourage the students that whatever you handwrite in here, you will be able to use on any quiz, any test, any midterm, any final. Open notebook, okay? But it has to be whatever you handwrite in here. You can't take Post-its and stick it in here. You can't take printouts and tape it in here. anything that you handwrite, either in this composition book or spiral bound notebook or something, as long as it's handwritten, you are allowed to use that on any quiz, any test, any midterm, any final, for all the courses that we're together, okay? And so you'll find the neater that you write after the lectures, the more useful this will be in the weeks and weeks to come. So this is one tip for success. One more tip for success is, I also specified this in the syllabus, is repurpose a binder. Somewhere in your house you have a binder. You don't have to buy a new one, but somewhere in your house you have a binder. And so just repurpose it. What are we going to do with the binder? What you're going to do with the binder is all of the worksheets that you are accumulating, you should be putting in here, and then they should be tabbed on a weekly basis. So I have a week 1 tab, week 2 tab, week 3 tab, week 4 tab, and for tabs for each of the weeks we're together. And if I open up week 1, this should look familiar to you. Sorry. This is one of the homework sheets from during the course of the week. You print it out, you've taken a picture of it, you've uploaded it, or you've done this in electronic copy, and you've sent it to me, and I've reviewed it, and I've made comments where the answers were correct and where some of the answers that were not correct. But what you ought to do is you ought to accumulate all of your work into the 3-ring on a weekly basis as we go through the semester. The binder in its entirety is worth several hundred points at the end of the semester. You're not to use the binder as an open resource for quizzes or tests, but this is a method by which you're going to establish a discipline, a personal discipline for keeping your information in chronological order. And I show that I'm moving around. All right. Okay, so anyway, this is worth several hundred points, and we will be doing a binder check in a couple of weeks to make sure that you are keeping track of your stuff in a 3-ring binder. So like I say, you don't have to buy a new one. You have a binder somewhere in the house, repurpose it for these 8 weeks, put in dividers, and start jamming in your stuff, okay? Okay, enough said about note-taking and that type of stuff. Let's go back to my share screen.
Sorry, really quick. What happens if we don't have access to a printer?
If you
Because
don't
of COVID, everything's closed and
I'll have to think about that. Yeah, we don't have public libraries to go print, and it's really awkward to do. If you, yeah, we don't have the school library.
I wonder if we could like sort our files into a Google Drive folder with like weeks 1, 2, 3, 4, and then share that with you.
Who came up with that suggestion?
That was Jess, my
Hey,
camera's
Jess.
off.
Oh, okay,
Hi.
great. No, so everybody hear Jess's suggestion to put everything in a Google Drive folder and then share that with me so that I can see that your information. And I think Jess and other people had brought this to my attention also. There was a request in my making the homework assignments available not only in my typical MS Word, but making it available in PDF format. And
That was me.
yeah, thank you. And starting this week, I will be happy to do so. Anything that I generate in MS Word, I can easily convert in PDF, and therefore it may be easier for you and a number of our other friends who don't happen to have Microsoft Office, that everybody can open a PDF and work from that. So I like your suggestions and ideas that if we don't happen to have a printer, Google Docs, and put it in a Google folder. The key thing here is you gotta show an organization of archiving your work content. And as I say, whether you show it to me in terms of Google Docs and individual folders per week, or you show me flipping through an actual binder, it is worth several hundred points by the time we get to the end of the semester. So it is well worth your effort. Several hundred points, I kid you not, because our the circuit builds circuit A, B, C, D, and E. That was a 100-point exercise in and of itself. The Khan Academy was a 120-point exercise of the 12 tasks in and of itself. This binder is worth several hundred points. So start working on organizing your work, okay? Okay, so going back to share, let's go to the next slide. And the next slide is here. All 12 formulas are spelled out for you. From the first circle, I get 3 formulas. V is equal to I times R, I is equal to V over R is equal to V over I. The second circle, so the first circle and the second circle are what we're going to primarily use for the next bunch of weeks. I give you the third and fourth circle formulas and their derivatives as a point of reference. But don't be intimidated. We're really working mostly from the first 2 circles. So at most, these 6 formulas. And like I say, if you write them into your notebook, you always have a ready reference for which formulas you're going to need for what. Let's talk about how we apply this. And here's where we will need to use your calculators. I give you a series circuit, again, simple circuit, 1 voltage source, 1 resistor. And I say if voltage is equal to 15 volts and R is equal to 5 ohms, I'm looking for I, current. The formula for I from the first circle is V divided by R. V is 15 volts divided by R of 5 ohms. What's 15 divided by 5, my friends? 3 amperes. That you can do in your head. Now, if I wanted to calculate for power, I can calculate power using the very first circle formula. P is equal to I times V is equal to 3 amps times 15. What's 3 times 15, my friends? 45. But what are the units of power? Watts. What is the symbol for watts? Capital W. Okay. And I put down or for the next bullet point. I could use the second circle formula for Watt's law, the third one in our sequence. P would be calculated as I squared R. I squared, I is 3 amps, square it is 9. 9 times 5 gives you how many watts? 45 watts. Same power as the first circle for power. The last circle for power uses V squared divided by R. I gave you the V at 15 volts. 15 squared divided by 5 ohms works out to be 225 divided by 5. Guess what? 45 watts. So this goes to show, as long as my circuit parameters are consistent, I can use any one of Watt's circle formulas and calculate the same amount of power. Okay, they all, basically what we end up doing is we could use power circle 3, power circle 4 to double check the very first power circle. Let's look further. You get to practice. Here's where you need your calculators. Okay. If in the above, I give you I is equal to 3 amps, V is equal to 6 volts. You have an I and a V. How do you calculate for power? Use the first circle for power. P is equal to I times V. 3 times 6 volts gives you how many watts? 18 watts. Now, in the second bullet point, if power is equal to 18 watts and current's equal to 3 amps, what's my resistance? Resistance would be given as P divided by I squared. Works out to be 18 divided by 9, which works out to be 2 ohms. You can take your time and go through these calculations afterwards, and let me walk through these with you. Now, if I say R is equal to 2 ohms, and earlier we calculated 18 watts, I'm looking for V, just to verify V. V is equal to the square root of P times R, the square root of 18 times 2, which is the square root of 36. And the square root of 36 works out to be how many volts? 6 volts. So this brings us back to the original given 6 volts. If your original circuit parameters are sound Each subsequent step of calculations you make will ultimately bring you back full circle to the original given value. We'll do this one more time. If this is a different, same circuit, but different set of numbers. Now current is 5 amps and voltage is 20 volts. How, using the very first P circle, P is equal to what? I times V. I is 5 amps, V is 20 volts. 5 times 20 gives you how many watts? 100. Now, power above. Power. Somebody please mute your microphone. Javier, mute your microphone, please. Thank you. All right. So power is equal to 100 watts. I is equal to 5 amps. So you got a P and an I. I'm looking for R. R would be calculated as P over I squared. P of 100 watts divided by 5 amps squared. So 100 divided by 25 works out to be how many ohms? 4 ohms. I'm going to jam this into the next line. R is equal to 4 ohms. Power of 100 watts. I'm going to confirm my voltage. Voltage is equal to square root of P times R. 100, square root of 100 times 4, square root of 400 works out to be 20 volts. That brings us back to the original given of 20 volts. These are called laws because as we go through them, if we go through them in this sequence, you should be able to confirm each of your calculations and it brings you back to one of the original given values. You get to do more. Next slide. We just did, okay. Here's, let's see, we did this, okay, now here. All right, engineering notation is also known as metric notation. The words are used interchangeably. Sometimes I'll say engineering notation, sometimes we'll say metric notation. They are identical. Why do we use engineering notation? It's the standard of the world, not just the US. It's the standard of the world to express large quantities or very small quantities efficiently. So let's go ahead and review decimals and let's review scientific notation. This page is the reason why Khan Academy was assigned a week and a half ago, 2 weeks ago. Some of you were communicating with me as early as 3 weeks ago and started with Khan Academy. Academy is an incredible free resource that gives us a refresher of background math that helps prepare us for this page. So using Ohm's law, if we have a voltage source that's 10 volts, resistor that's 470 ohms, so with your handy dandy calculators, we're going to calculate this right now. We want current. So I is equal to V over R. When you calculate 10 divided by 470, many of your calculators are still set in the decimal mode, and it's not uncommon to see a decimal number similar to this. Now, this has not been rounded off. I think it works out to be 22. Let me do this because I did this much earlier with a rounding function. So divide by 470. Yeah. So this is 26595. So 6595. 7. Oop. Okay. Big long decimal. And so on your calculators, 65957. Decimal notation is shown with as many digits that your calculator can display. In Khan Academy, you were practicing something known as scientific notation. And scientific notation is represented this way. And I'm going to highlight this in yellow. It's represented by one digit, followed by the decimal point, followed by the rest of the numbers, and then followed by the power, and then the unit. So if I take this number in decimal and in the calculator, I convert it to scientific, or we do it manually. We won't do that now. You did that in Khan Academy. You would end up with a scientific notation that is 2.12, and I could type in all the rest of the digits, but I'm going to lose my line. But it works out to be times 10 to the power of -2 amps. So do I have a power of 10 -2? And do I have an electrical unit of amps? Now, in engineering notation, it works out to be 21.277 times 10 to the power -3 amps. Could be written as, oops, there should be a decimal point here, not a comma. Decimal point, 21.277 milliamps. And then if I round this off to 2 digits after the decimal point, it works out to be 21.28 milliamps if I round this properly to 2 digits after the decimal point. It begs the question, what is this thing called milli? And what do we use for, what symbols do we use for engineering notation? Is shown in this slide. Here you go. And here's another thing that you want to include in your notebook. You have a column for symbols. Capital E, capital P, T, G, M, lowercase k, M, this thing that looks like a U, N, P, F, A. Then you have the metric prefixes as to how they are pronounced. You have the powers of 10, and then the value in English terms. I point your attention to the powers of 10. Look at the exponents in the powers of 10. Are they all multiples of 3? 10 to the power of 3, 10 to the power of 6, 10 to the power of 9, 10 to the power of 12, 15, 18. 1 is 10 power of 0. And then going on the other side, going into smaller increments, you have 10 -3, 10 -6, -9, -12, -15, -18. Again, multiples of 3 for these exponents. And so I have in this big illustration over here, the base is 10. This little number as a superscript is the exponent. The combination of the base with the exponent is known as a power. It's a really nice picture. So I need you to really focus most of your attention between trillion down to, say, trillionth. That's where most of our work will be. So follow this with me. Capital T, the metric prefix is pronounced tera. Everybody say tera. And tera has a single R, not 2 R's. Tera with 2 R's represents Earth. Then you have 10 power of 12 trillion. How do you, what's a memory tool you can use for this? Tera starts with Tera is the letter capital T. The symbol for 10 power of 12 is capital T. The word is tera, which starts with the letter T. The power is 10 power of 12. 12 starts with the letter T. And the English term is trillion. Trillion starts with the letter T. So you get a bunch of T's on that row. Hopefully that'll help as a mnemonic. Next one is giga. G for giga, capital G. It's pronounced as giga, not giga. And 10 power of 9, and that's billion. Then you have capital M, that's mega, 10 power of 6, million. A lowercase k for kilo. And the kilo is one of the most common things that everybody encounters. If you were in middle school and you were in high school and you were required to run around track, if you had physical education, you ran in kilometers, okay? And a kilometer is 1,000 meters. So that's 10 power of 3, which is 1,000. Now for 10 power of 0, units of ones, there is no prefix, there is no prefix symbol, okay? That's why they're grayed out. When we go to the negative side, 10 -3, which is in English terms, thousandth. So compare. 10 to the positive 3 is thousand. 10 to the negative 3 is thousandth. Add a th. In engineering terms, this is called milli, 2 L's, lowercase m. Take a look at 10 negative 6. 10 negative 6 is called what? Millionth. What is 10 positive 6? Million. 10 negative 6 is millionth with a th. The engineering prefix is called micro, and the symbol looks like a cursive U. When I type this out, I will actually use the letter U from the keyboard, lowercase u. Then you have 10 negative 9, which is billionth. 10 positive 9 is billion. 10 negative 9 is billionth with a th. This is pronounced as nano. So when they're talking about nanobots, they're talking about robots that are so small that they can fit into your bloodstream and do all kinds of wonderful things that the physicians want those little critters to do. Those are nano. Nano's pretty small, billionth. And the symbol for nano is a lowercase n. Then 10 negative 12, trillionth. What's 10 positive 12? Trillion. 10 negative 12 is trillionth. What is the metric or engineering prefix? It's called pico, lowercase p. So as I say, most of our work will between trillion down to trillionth. 10 positive 12 down to 10 negative 12, okay? What does this mean on your calculator? Let's see how this applies. So now we're going to reset your calculator. If you are using something other than what I specified in the syllabus, for details of how to use your calculator, you will have to refer to your owner's manual for your calculator. And if your calculator is a Texas Instruments, Hewlett-Packard, Sharp, Casio, you'll have to refer to the manual. Since this is the calculator specified in our syllabus, the documentation in our PowerPoint will be specific to this one. The functionality that we want to achieve will be the same for all your calculators. First thing you ought to do is reset the thing. Whatever has been set up, you can reset. And how we reset on this is done by these steps. We turn on the thing, we go to number 2, clear the display. Number 3, we hit the shift key. Number 4, you hit the mode CLR key, and that's specified here. Turn on the calculator, clear the display, shift key, and then hit the mode CLR key. When you do that sequence, you will see this display that shows these options. Here, you want to press 3 to select all. Then you will see this display. Then you will click the equal key at the bottom right of your calculator to enter the reset all function. Then you will see this screen that tells you, yes, it is setting all. You hit equal to actually engage, enter, and reset. And when everything is said and done, you have this display. This is now reset and ready for the next step. So as I've said, if you're not using this particular calculator, refer to your owner's manual, start with the reset. Next, scientific calculator. Oops, too far. Here we go. We're now going to set this to degrees function. Your calculators can calculate in terms of degrees, radians, or grads. So at this point, we're going to be consistent and set our calculator to the degrees mode. So first thing you do is you press the mode key, and then we will see this. If I press the mode key again, I will see this option. At this point, I want degrees. So I'm going to key the number 1, and then I do so, I will now see this. And here, there will be a little tiny D in the top of your LCD. Your display screen should show a D, not an R, not a G. R stands for radians, G stands for grads. We want degrees. That part is done. Next step, we're going to set to scientific notation. So here it says we're going to press the mode key how many times? According to my directives, you hit the mode key 3 times and you will get to this screen. Which one of these options is associated with scientific? 2. So you press 2. Then what you see is this screen. What it's asking you here is in the scientific notation mode, how many digits do you want to fill your screen with? Well, if it gives you 9, press 9. You want to fill your display. Then you will see this. When you see this, you want to make note of, you will see SCI on the top of the screen for scientific, on the top row of your LCD, and on the bottom, you will see all the digits, and on the far right-hand side, you will see times 10, and then 2 large zeros for where the power is going, where the exponent's going to be. And this will appear in the lower right-hand corner of your display. Now, let's talk about conventions. Conventions on what we're going to use. Rounding off rules and something known as proper engineering notation. As a review, we will round all of our answers to the 100th decimal place. This means how many digits after the decimal point? 2 digits after the decimal point, not to the 10th. And some of you did this in your homework that you turned in. You were asked to do some calculations for Ohm's law, and I saw some numbers come in as 2.10 or 1.7 instead of 1.67, and I pointed that out to a number of you. The directions clearly state 2 digits after the decimal point, proper rounding. So I thought I'd include this in here. And when you get this PowerPoint, and I will load up the PowerPoint before the end of this evening, when you get this PowerPoint, there happens to be 2 YouTube videos that both will refresh you on how to round to nearest 100th. So if, for example, your calculator shows this number of ohms, 34.35621, your rounded answer should be rounded to 34.36 ohms. So those examples in the YouTube will guide you to proper rounding to the 100th. Then there's another convention we use in technologies, and that is known as proper engineering notation. What makes proper is this, first line. Proper engineering notation is identified with only how many digits in front of the decimal point? Only 1 to 3 digits in front of the decimal point. Between what? 1 up to 3 digits in front of the decimal point. Next bullet says proper engineering notation is never shown as a 0.0xx decimal quantity, such as 0.0345 kilovolts. Proper engineering notation will have no decimal. It'll be a whole number in front of the decimal point. Next bullet. Proper engineering notation is never shown with 4 or more digits in front of the decimal, such as this, 2,793.9323 milliamps. Take a look at the decimal point. How many digits do I have in front of the decimal point? 4. That is a no-no. We don't show anything except 1 to 3 digits in front of the decimal point. So do this as a calculation. If you do this as a calculation right now, 1.6 divided by 4,700, and I'm going to do this with you. On my calculator, your calculator, 1.6 divided by 4,700, turn it on first, Co. All right, now that it's on, 1.6 divided by 4700, hit equals. When you hit equals, your display of the calculator is set up for scientific notation. You should see this, 3.40425532 times 10 to the negative 4. And you write down amps because that's the unit of current. Is this an engineering notation? No, the giveaway is, look at the power of 10. The power of 10 is a negative 4. All engineering prefixes are going to be exponents that are multiples of 3. So what you're going to do, on your calculator, this particular one and other ones I suggest like it, there happens to be a key called ENG. Hit it. When you hit the ENG key, the calculator will automatically shift the answer to give you the correct multiple of 3. This works out to be 10 - 6 amps. And it gives you this decimal, 340.425532 times 10 - 6. And we would write down our answer on an answer sheet in proper engineering notation with 2 digits after the decimal point. This will be written as 340.43, and 10 - 6 is the symbol that looks like a lowercase u, micro, and the unit of current is amps. Okay. And on that note, I will go ahead and give us our overdue break. I apologize. So I will go ahead and put us on timer. And while we are on break, I will take care of bookkeeping like roll call. And you can also throw questions at me during this break time. Let me go ahead and put on a quick 10-minute timer here. Start. Okay, we're on break for 10 minutes. Let me go ahead, get the roll sheet, and start. We're on a break. I bet you somebody has some questions. Wait till you see the circuits we're building. Oh my gosh, they're fantastic. Absolutely fantastic circuits.
Professor, I had a question about Canvas.
Yes.
So I did the introduction, discussion, and reply, but on Canvas It shows up as missing, even though I got points for it, and I did it.
You received points, which means I reviewed it and I saw your responses, so you were marked for points, but it shows up as missing?
Yeah.
Okay, so here's the thing. Canvas does do some strange things. The important thing is the points. As long as you have received points for it, that's what counts. And last week we had a total of, what were our deliverables? Like 460 points total. So what you ought to do, all of you, is you go to Canvas, you go to grades, and you look at the number of points that you've accumulated in the first week so far. And if you're at what I put down as the total number of points possible for the first week, and I believe that was some number around 460. And if you're there or in excess of that, because some people have received bonus points for being so helpful to other classmates in Discord and on the chat and things of that sort, you're in good standing. If for whatever reason we're missing big chunks, then during these break times or after our session this evening, we can have a catch-up discussion and say, okay, Co, I turned in this, and unless Co is horridly behind for some reason, all of the major point items you should have had accounted for. Now, some of you, if you go to check your Canvas, say, oh my gosh, out of 465, I only got 360 something. Well, that's because one or two of you have not yet received all of your parts, your electronic parts. Not everybody's turned in their circuits. Oh, that's a reminder. This is really important. Remind me when we come back from our break. Remind me to ask me, what is my middle name? Some of you I share that with. And so when we come back from break, when everybody's on, it's very important that everybody understands what Frank Coe's middle name is. It'll be helpful to all of you. And I did share that with some of you. So any other questions so far while we're on? I think there's 7 minutes left on the break. Okay, I'm going to give you a sneak preview. There is circuit build F. Make that as big as I can for you. And magnify it here. It's not a, can you all see the circuit on the screen? Give me a thumbs up if you can see the circuit. Cool. So as you're looking at the circuit, you're going to be introduced this week to series circuits. We're putting components together, not just single resistors. We're putting multiple resistors together. And in this circuit, I've got two resistors, an R1 and an R2, and I've got very specific connection points in between them labeled as A, B, C, D, E, F. There's a switch in here, there's an LED in here, there's going to be a 5-volt source in here. And if we take a look at how it's laid out for you, hi Chandler, welcome. Thank you. Glad you could make it. All right.
Hi. Good
The
to be
first
here.
part of this is, yeah, that's great. Yeah, the first part of this is recorded, so have no fear. I just thought since you came in on a break, I just thought I'd give our classmates a preview of circuit F. And circuit F looks busy, but it's actually just two resistors and a switch. I threw in the LED in here only because we want the LED in here when we push the button just to show that if the LED lights, then our circuit is built correctly, okay? When we go to do our measurements later for the circuit, the LED will be yanked out and no longer part of the circuit when we go to do our measurements. But the LED is here only as a visual aid when we press the button to show us that this is working. And I'm going to build this circuit with you after one of the next breaks. I'm going to be building a similar circuit. We'll be building this one because you're going to be building this one. I'm going to be building a circuit with, I think, a 100 ohm resistor and 330, I think. I'll measure it and see. In any case, very, very interesting circuit. Lots to talk about. And very important that I label these points specifically. Point A in this upper corner is connected to the positive side of my voltage source and the first resistor. Take a look at point A. So where does point A sit on the board? Point A on the board sits as your red rail. Your red rail, remember the power supply at the top here is your 5 volts. The lower jumper wire here is in the off position. So we're only using a single 5-volt source, which means I'm powering the red rail with this. And so that's where my positive side of the voltage source is sitting. That's point A. Point A is also where the resistor connects to power. So the resistor connects to power here. So point A is actually on the rail itself, as well as this side of the resistor. On the other side of the resistor, in the schematic, the other side of R1, I have R1 connected to R2, and that's identified as point B. On the circuit build, I'm using a jumper just to space things out. And so where the first resistor is going to connect through this jumper to the second resistor, one end of that jumper is point B. The other end of the jumper is also point B, because there's no resistor between this end of the jumper and this end of the jumper. If I go to measure that, it's almost 0 ohms on that bare piece of wire. So point B can exist here on the right side of the first resistor. Point B is also found on the left side of the second resistor. So there are 2 points where I can measure point B. I will talk more about this circuit in a little while. All right, our time is up. Let me go ahead and mark Chandler as being present. So Chandler.
Professor Go, I had a question.
Yes, Andrew.
It's in regards to the homework, but I did a lot of the reading. I wanted to find out what your preference was as far as the electron flow versus conventional flow for the circuit. It seemed like people were kind of back and forth based off their own opinions on their theories and stuff.
For most of our 8 weeks together, our emphasis will be mostly on electron flow. But it's very important that you understand conventional flow as being exactly opposite in terms of direction to electron flow. And depending upon how arrows are drawn in certain illustrations, you should recognize one being electron current flow and one as being conventional current flow, okay? So most of our work will be to emphasize electron current flow, and I think that where there is some ambiguity, then the arrows. Hi, Frank. Thank you for joining. Could you mute your microphone, please, Frank? Thank you.
Yes, sir.
Thank you. All right. So to answer Andrew's question is we're going to see electron current flow and conventional current flow many times during the course of the weeks to come. And so given an illustration that shows the plates of a voltage source and arrows that are drawn around the schematic, any arrows leaving the positive plate, that's conventional current. Any arrows leaving the negative plate is electron current. So however it's specified is how you will answer the question, okay? Okay, all right, let's move on. Let's take this circuit off the share and get back to our PowerPoint. And here's the next thing in our PowerPoint. Okay, what are the requirements for a circuit, my friends? The requirements for a circuit are pretty basic. You have to have a voltage source. Why? The voltage source provides the what? Pressure to move electricity. Without pressure, electricity is going nowhere. So you have to have a voltage source. Next thing for circuit requirements, you have to have connecting wires. If you don't have connecting wires, you don't have the pathways for the electricity to flow. So you need a voltage source and you need connecting wires. That's two. The third thing for a practical circuit is you have something called a load. Okay. L-O-A-D, load. What is a load? A load is any device that has electricity flowing through it. Now we don't say wire. Wire is not considered a load unless it's really, really long. In our cases, the wires are short, so they're not considered a load, even though they have electricity flowing through it. So the word that's used in this line is any device. So what type of devices have electricity flowing through it? Well, what you have in your kits that we've built so far happen to be LEDs, and LED would be a load, and a resistor would be a load, okay? Then, for a practical circuit, the fourth thing is something called continuity. Continuity is essential for the current to actually be able to flow. And I give you a definition for continuity in a little bit, but I'll tell you right now, continuity simply means a complete path for electricity to flow. Take a look at these two illustrations. The circuit on the left has the first three requirements. It has a voltage source, it has connecting wires, and it also has a load. So it's got 3 out of 4. However, it has no continuity. Why? Because the switch is shown in what position? The switch is shown in the what we call open position. Open switch means no continuity, means we do not have a closed path for electricity to flow. Take a look at the circuit on the right. The circuit on the right has all 4 circuit requirements for a working circuit. It has a voltage source, has connecting wires, has a load, and most importantly, it also has continuity, which is demonstrated by the switch being closed, much like your light switch. So on the wall in your room, if the light switch is open, you have an open circuit. No electricity flowing, no continuity, no lights in the room. On your wall, you close the switch. When you close the switch, you have lights. Why? Because the circuit between the light switch and your light bulb has connecting wires, you have continuity, and the lights light up. Are we good with this so far?
Yes.
Next, series circuits. We're going to talk about series circuits and we're going to talk about parallel circuits. Most of the emphasis this week will be on series circuits. And if you look at this, fundamentally, you want to write this down. Series circuits have one current path. If you write down anything, you write down series circuits have one current path. And so for Mr. Sepulveda, Mr. Chandler, Frank Sepulveda, and Mr. Chandler, I held up this earlier as a recommendation for all of the students to acquire. It's part of your syllabus, a bound notebook of some sort. This one happens to be a composition book. This is bound, this is paperback. This one happens to be in graph paper format. And what I said to the class earlier is whatever you handwrite in here neatly after the lectures, all the formulas, all of the charts, all of the terms, whatever we do in our PowerPoint slides, you handwrite in here. You can use this on your quizzes, tests, midterms, and finals for the duration of time you're in our program. Plus, it's a really good way to keep all of your concepts together. Now, that doesn't mean you're going to take a Post-it or one of my papers and jam it in here. That's not, no, you can't, that's not permitted. Everything you do in here has to be handwritten. Then you can use it, okay? So no papers are added to this, so whatever you write. And so what are one of the things you're going to write down? Probably this page, this concept page. So series circuits are identified as how many current paths? 1. And if we take a look at the light bulbs show a battery. And here's a good one, Mr. Goodson, you asked this question. I have these arrows that are drawn leaving the positive side of this battery. So if the arrows are drawn leaving the positive side of this battery, going through these light bulbs, coming back to the negative side of this battery, which model current is being shown in this particular illustration?
The conventional current.
Precisely. If it's leaving the positive side of the source, it's called conventional current. What is the other name for conventional current, my friends? AKA whole current. Whole current. Okay, conventional current is also known as whole current. Okay, so this happens to be conventional current. Electrons would just simply flow the other way. The important thing about this illustration is how many paths do you see for the current to flow? There's only one. Take a look at the schematic. The schematic shows what, instead of a 1.5 volt pen-light battery, it shows these alternating plates. This is a DC voltage source, 9 volts. And I happen to have 3 resistors. And the electrons in this circuit, the one on the circuit that's on the left side of the slide, electron current will flow in which direction? Is it clockwise or counterclockwise?
Counter.
Clockwise.
It would be counterclockwise.
Negative to positive.
On the left-hand circuit, electron current leaves what plate of the voltage?
The negative.
Electron current leaves the negative plate, so electrons will flow down, then to the right, then up, then to the left through the resistors to the positive side of the source. So as it flows in this direction, that is called counterclockwise, and we would abbreviate that as CCW, okay? In which direction does conventional current flow in this left-hand circuit? Conventional current would leave what plate of the source? Positive. So conventional current will leave the positive and flow through the resistors down to the left, back to the negative plate. So what direction would conventional current flow in this left-hand diagram?
Clockwise.
Clockwise, okay? Very important we get used to using those terms. Next, let's go through the bullet points. Series circuits divide something. What do series circuits divide? Voltage, that's what it says, yeah? Series circuits have a nickname. They're known as what type of dividers? Voltage dividers. We add in here string. String. Series circuits have a nickname. They're also known as a string. Why string? Because if you think of a string of pearls, grandma's string of pearls, whoever still does wear pearls, it's one bead in a string to the next bead in the string to the next bead in the string. It's one string that links all the beads together. That is the nickname that's given to series circuits. Series circuits are known as a string, and they divide voltage. They're known as voltage dividers. Now, since there's only one path for electricity, take a look at the third bullet point. The third bullet point says, what is the same throughout a series circuit? Current is the same throughout the series circuit. If you take a look at this left-hand diagram, this 9 volt with the 100 ohm and the 300 ohm and the 50 ohm, the electricity flowing between the first 2 resistors is the same amount of current that flows between the second and third resistors, is the same amount of current between the third resistor back to the source. the current, no matter where we measure in this circuit, will be the same throughout the series circuit. That's absolute. And if we take a look at the formula on the right-hand side, that's evidenced by the formula. The total current is equal to current through the first resistor, is equal to the current through the second resistor, is equal through ... to IRN. What does the N mean in the formula? It means however many number of resistors I happen to have in series. Now here's a very interesting concept, this fourth bullet point. It says here that the largest ohmic resistance will, in the terminology in parentheses, quotation marks, drop. The largest ohmic resistance will drop the highest amount of voltage. Which one of these three resistors has the largest, is the largest ohmic resistance? What can you see there? 100 ohm, 300 ohm, and 50. Yeah, R2. R2 is 300 ohms, and it surpasses the other two. If we go to calculate the amount of voltage across R2, and we go to measure the voltage across R2, it will be the highest amount of voltage of the three. The smallest ohmic resistance will drop the smallest voltage. Which one of these is the smallest ohmic resistance? R3. It's only 50 ohms. If we go to calculate the amount of voltage on it, it will be the smallest. The next bullet point, very important. Voltage drops are proportionally distributed across series resistors. The voltages that we measure across these resistors is going to be divided proportionally. So that 9 volts is going to be divided. A chunk of it will be across R1, a chunk of it will be across R2, a chunk of it will be across R3. The biggest chunk will be across R2 because it has the biggest ohms. The smallest chunk of the 9 volts will be across R3 because it has the least amount of ohms. We'll show you these in numbers in a little bit. And then if you think about this chain of lights, the circuit will be what? Off if there is a break in the circuit. If we break the circuit anywhere in the series circuit, like light bulb goes out, they all go out. They don't burn out, but they all turn off if one light bulb burns out. And you might remember this, for those of you who are a little older, Grandma's Christmas lights. If one light bulb burns out on that string of Christmas lights, boom, they all go off. And it was a pain in the butt to have to find the one light bulb that went out. Newer light bulbs, newer Christmas lights are not wired that way. Take a look at the formulas. V total in a series circuit is the sum of the voltage dropped across R1 plus voltage across R2, R3, all the way to Rn. What does the N represent again? The last number of 3, 4, 5, 6 resistors. The current, IT, is equal to IR1, equal to IR2, equal to IRN. The current is the same throughout a series circuit. R total, how do you find R total? Well, guess what? We add the ohms together. So R total is the sum of R1 plus R2 plus, in this case, R3. If we add these together, how many ohms do we have? 100 plus 300 plus 50. How many do we have? Mama's math. Somebody give me a total without using your calculator.
450.
400. Exactly.
450.
450 what?
Ohms.
Ohms. Okay, very important. I got to get all of your classmates in tune with saying the appropriate electrical term. So it's not just 450, it's 450 ohms. Okay, now, power total. Each one of these will generate heat. If I put my hand on the circuit, some of these resistors will be warm, some may even be hot. So as they generate heat dissipated, power dissipated in the form of heat is power. So total power is equal to the power dissipated by R1, the power dissipated by R2, power dissipated by R3. So if I calculate each of the power given off by each of these resistors in the form of heat, total power is simply the sum of all three powers. The most significant formula of the bunch is this one here. Voltage divider formula equals VDF. And let me widen this just a touch so we can see this on one line. VDF is the abbreviation for voltage divider formula. And if you look at this formula, it's a very easy formula. It tells you that the voltage across a resistor called X is equal to the value of that resistor Rx divided by the total times the voltage source. It's a fraction. All that is basically a fraction. What fraction of the source is going to be across a particular resistor? What fraction of that 9 volts is going to be across that 100 ohms? So let's do this. I don't have it spelled out for you, but look at this formula. If we want the voltage across the first resistor, we're not going to use Ohm's law. We're going to use this fractional formula. It says right here, if I want the voltage across the first resistor, VR1, VR1 is going to be equal to R1 over the total of ohms, and then multiplied by the source of 9 volts. So this would be in my fraction, 100 ohms over the total of 450. So 100 divided by 450 times 9. Do that on your calculators, and I'll repeat for you. Turn on the calculator, type 100 divide by 450, and then multiply by the 9 volts. Boom! What does your calculator show you? Luis, do you happen to have a number for me, my friend? What do you got, Luis?
Yeah, I just have 2.
2, yeah, and it would be 2 volts. It works out to be 2 volts.
Yeah.
Let's try this, my friends. I want the voltage across R2, and again, I'm going to use the fractional formula. If I look at this fractional formula, VR2 is going to be equal to R2 over the total times the 9. What's R2? 300. What's my total? 450. So the fraction is 300 divided by 450 times 9. So I'm going to do 300 divided by 450 times 9. Ryan, do you happen to have a number for me, Ryan? How many
I
volts?
got 6.
And that works out to be 6, and the units of voltage would be?
Volts.
Good, yeah, because we don't never just say the number. It's 6 volts. Okay, I'm trying to get you all to say the electrical term, not just the number. I got 6, which is great. Yeah, 6 is correct, but 6 what? 6 apples, 6 oranges, 6 volts. Very good. We're going to do the last one using this fractional formula, voltage divider formula. I want VR3. To calculate VR3, what do? I take R3 divided by the total of ohms times the 9 volts. What's R3? 50. Oh, wait. 50 divide by 450 times 9. And this works out to be how many volts? Anna, do you happen to have that for us, Anna?
1 volt.
1 volt. How many people agree with 1 volt? Cool. So we did you're right, absolutely right. Thank you, Anna. So we calculated the voltage drops across each of these 3 resistors using voltage divider formula. We did not engage Ohm's law. We did not engage Watt's laws. We can calculate these voltages with a different method, voltage divider formula. Very profound. Next, any questions on this? We will.
Is that only for series?
That's only for series.
Okay.
Yep. Any other questions? Okay.
Question.
Yep. Please go. Who has a question?
Me.
Yes, go ahead, Kristen.
So
Kirsten.
for the voltages, sorry, I'm a little confused because, okay. So when you say V total equals the voltages added up, those are the voltages you got from the voltage divider formula?
Yes.
Okay.
The 2 volts plus the 6 volts plus the 1 volt add up to 9 volts.
Got
Sweet.
it. Okay.
And that's our proof that our numbers were calculated correctly. We individually calculated 2 volts on the first resistor. We calculated 6 volts on the second resistor. We calculated 1 volt for the third resistor. And according to this formula, the VT formula on this page says the total voltage better be equal to the sum of the individual voltages. So the 2 plus the 6 plus the 1 give us a total of 9 volts. We're happy.
Thank you.
Okay, good question. Any other questions on this page? We will get deeper into each of these formulas the more we practice. Another question?
Can a wire chew up voltage?
Can a wire have, only if it's really, really long, Mr. Sepulveda, only if it's really, really long. The wires that we're using on our boards are so small, so short, they're basically 0 ohms. The ohms are so small, they're going to be inconsequential. So what tiny, tiny amount of voltage that actually will be dropped across the wire is so insignificant, we basically ignore them. But is there resistance in wire? The answer is yes. Is there resistance, a lot of resistance in a really long piece of wire? The answer is yes. So when you think about the school library as an example, is there a wire to every computer linking that computer to the internet? Yes. That wire is a maximum of 100 meters long. That means that wire can be a maximum of the length exceeding the length of a football field. That long length of wire, you betcha there's going to be some ohms and there's going to be some voltage that we're going to lose across that. But in the work that we're doing, you and I are doing, the wire voltage is so tiny, it's basically nothing. Okay, good question. Did that answer your question, Frank?
Yeah, it did.
Okay,
Thank
good.
you.
Any other questions? You're welcome. Any other questions before we move on?
So would we use one of the previous formulas like Ohm's law to calculate current?
We will.
Okay.
Yeah. Yes, we will. Yeah, the question was, could we calculate current and power and other quantities using the other circle formulas? We will. But I wanted to take a moment and show you that there was one very special formula known as VDF. And VDF is an abbreviation for voltage divider formula. And it shows you in the formula how voltage is divided according to this fraction. What fraction of the total is going to be across any one of the individual resistors? It's a really powerful formula. Good questions. Let me move on to parallel circuits. Okay, beyond this one page, I won't be talking more about parallel circuits, and I have one more formula to jam in here, and that's current divider formula. But parallel circuits are here. And parallel circuits divide something. Parallel circuits divide current. Parallel circuits are known as what type of dividers? Current dividers. What is the same across the branches of a parallel circuit? Voltage is the same across the branches. So look at my illustration here, the circuit that's shown 9-volt source. Is the top of each of these resistors connected to the top of my source? Yes. Is the bottom of each of these components connected to the bottom of my source? Yes. So if I go to take my digital multimeter and I measure across each of these resistors, the voltage across each of these resistors, they're all going to be 9 volts. This 9 volts is across R1, is across R2, is across R3, which is evidenced by the formula here. V total is the voltage across the first branch, is the voltage across the second branch, is however many branches we have. The voltage is the same. Parallel circuits, okay, let's see, then I have here, the largest ohmic resistance will flow the lowest current. Which one of these is the largest ohmic resistance? The R1, it's got 10,000 ohms, 10 kilo. It will have the most resistance, which means it'll have the least amount of current. Remember, if you can see my face in the slides here, like the pedals of a bicycle, if resistance goes up, current must come down. If resistance goes down, current must come up. They behave opposite of each other, current and resistance. So take a look at my next bullet point. The smallest ohmic resistance will flow the highest current. Smallest ohms means least amount of resistance. It'll flow the most current. And the currents are proportionally distributed through the branch resistors. So whatever flows through the first branch, second branch, third branch, the amount that flows through each of them is proportionally distributed. And here, last bullet point, circuit will not be off if there is a break in any of the one branches, like the new Christmas tree lights. So in your new Christmas tree lights, if one bulb burns out, the rest of them are still lit because your Christmas tree lights are built in parallel. Take a look at my illustration on the right. It shows 3 light bulbs. All 3 light bulbs are hooked up to the same voltage source. The voltage that I measure across the first lamp is the same amount, which is the 1.5 volt battery. The voltage across the second lamp and third lamp are also 1.5 volts, because what's the same across the branches of the parallel circuit? Voltage is the same across the branches of a parallel circuit. Which one of these, so if the second lamp burns out, will current still flow through the first lamp? Yes. Will current still flow through the third lamp? Yes. But current will not flow through the second lamp if the filament is burnt out. This is how your current Christmas tree lights are set up. And that's all I want to say about this page now, because we're going to save the bulk of what's happening in parallel circuits really for next week. But I thought we need to have this in here just to show you that the 2 fundamental relationships we're going to encounter, first will be series, second will be parallel. All right. Then the next concept that you'll see as part of a homework question is something called series aiding and series opposing voltage sources. So take a look at the schematic that I have on the left-hand side. How many voltage sources do you see? 3. Take a look at V1. V is 5 volts, V2 is 5 volts, V3 is 5 volts. So if you read the text underneath the left-hand illustration, it says voltage sources are aiding in series if they are moving electricity in the same direction. Let me put this in quotation marks. They are said to be aiding if they're moving electricity in the same direction. Let's analyze each one carefully. Look at voltage 1, source 1. Which way does electron current move? Now, I'm specific in my question. I didn't say which way does current move. I asked you which model of current. I said electron current. So electron current from the first source leaves what plate? From the first source, electron current will always leave the negative.
Negative.
That's right, negative, which means it must first flow down, then flow to the right, then flow up. So this infers what type of directionality for the first voltage source. It wants to move electrons in the, I wrote down CCW, counterclockwise. Everybody in agreement with that? Take a look at the second voltage source, V2. V2 is at the top, center. And the electrons want to leave which plate? The negative plate. And if electrons leave the negative plate, which direction does V2 want to move electricity through the circuit? Also CCW, counterclockwise. Take a look at V3. V3, negative plate, far right-hand side, wants to flow electrons up and then to the right. So it wants to flow electrons in which direction? Counterclockwise also. Whoa. Are all 3 of these sources moving electricity in the same direction in this schematic? The answer is yes. And if they are moving electricity in the same direction, what is the relationship that is specified? They are said to be, I highlighted in yellow, what? Aiding. So these are series aiding. So the last bullet point at the bottom says, so the total voltage moving electricity calculates to be how many volts? You have 5 volts, and you add to another 5 volts, and you add to another 5 volts, giving you a total of how many volts? 15 volts total. They're spread out, but you have a total of 15 volts. And that 15 volts is going to be distributed between these 3 resistors. Take a look at the circuit on the right. Again, I got same resistors, 3 voltage sources, but have a slightly different arrangement. Voltage source 1, as before, moves current counterclockwise. Voltage source 3 moves current counterclockwise. But take a look at voltage source 2 closely. Voltage source 2 has the plates reversed. The negative plate is on the right-hand side. It wants to push current from the negative plate. So as voltage source 2 pushes current, it wants to move current in which direction? Clockwise. So here, according to the definition, this is described as series not aiding, but series what? Series opposing, because not all sources are moving in the same direction. So how do I calculate the total amount of voltage in this circuit? Would be 5 volts, add to a negative 5 volts, add to a positive 5 volts, gives me what net amount of voltage? 5 volts, not 15. 5 volts is my total, and that 5 volts will be divided amongst the 3 resistors. Any questions about series aiding versus series opposing? We're going to work out this next one. So what I encourage you to do is this. I encourage you to grab a piece of paper, and I'm going to grab a piece of paper, and we're going to work out, and this is what we're going to have. We're going to do VIRP. Just create a chart. We happen to have first resistor, we happen second resistor, 2, sorry, R3 total. Create that with enough space that you can write in some numbers. And the schematic that we had to play with was a 9-volt source, this is really crude because I'm doing this very quickly. I happen to have an R1, happen to have an R2, happen to have an R3, 100 ohms, 300 ohms, and 50 ohms. Give you a moment to catch up. Is this fairly large? Can everybody see this? Somebody put down, oh, Kirsten put down, is that why you Christmas tree lights are braided? Yeah, they happen to be braided as a consequence of the parallel wiring, because there's a third wire in there, and then so the easiest way for them to manufacture the Christmas tree lights and keep them from tangling is to braid them together. So the braiding happens to be a consequence of the parallel wiring. And let's see here. Physics usually uses conventional current flow. Good. Can you have a virtual notebook? Someone had asked that earlier, can we use Google Docs? And Google Docs would be a form of a virtual notebook. Whatever.
I think you mean
no.
like the one that we can use on the tests.
Oh, no. You cannot have a virtual notebook that you can use on the test, because the only thing you can use in your test is in the regular classroom is calculator, pen, and paper, okay? And the notebook counts for paper. Anything virtual in your phone or tablet or computer means you've got internet access, and that's a no-no on a proctored exam. Hope that answers that question. Let's see what else is in the chat. It says, will class still be meeting on Tuesday, or did we end up splitting the class? Okay, so somebody didn't, if you read my notation carefully, and I'll answer that while you're creating this chart. The majority of the class was in favor of splitting, but there were some people that were Tuesday only. And so what we're doing is, I put down a required 3 hours for the Tuesday. So we'll go through up till about 9, a little bit after if necessary, but up to 9, that's required. And then 1 hour on Thursday. And if you can't be there on Thursday, then catch the YouTube video for Thursday. But the reason for the split, and I've taught this class a couple ways in several different colleges, what I've always enjoyed is a split schedule during the week. And the reason for that is, as most of the lecture content is heavy during the first meeting, there's always follow-up questions that students have. And by having that second opportunity to meet later on in the week, it gives students the opportunity to absorb, digest the information, look at the PowerPoint, look at the video recording or audio recording of the lecture and say, oh yeah, I didn't quite get this because now I'm doing the homework assignment and now I really have a question. And so if we have that second meeting, it really does help a number of students, especially in this first semester class, to have that split. So that's why it was offered. And we're going to be doing things this way. So 3 hours on Tuesday, 1 hour, plus the extra hour on Thursday. So the 1 hour required on Tuesday, 1 hour required on Thursday, but I will go on till the 8 o'clock if there are additional questions that need to be answered. Okay, hopefully that answers your question, Abbas. And let's move on. Now, here we go. Everybody has this chart. The way you start this chart, you fill in the freebies. The freebies are your given quantities. What's a freebie? What is given? Well, my friends, take a look at this. What's given happens to be your ohms. Were you given R1 of 100 ohms? Yes, you write that down, 100 ohms. Were you given R3, R2? R2 is 300 ohms. You write that down. Were you given the value for the third resistor? It's 50 ohms. You write that down. In a series circuit, what is my total amount of ohms? If you refer back to your notes, it's the sum of the individual ohms. We actually did this earlier. The total amount of ohms was how much? 450 ohms. Woohoo! What else is a freebie? The 9-volt source that you're given. Boom. From here, before you go to fill in anything else, make sure your freebies are filled in correctly. Is the value of the 100 ohm resistor for R1 in the R1 row? Is the value of 300 for R2 in the R2 row? Is the value of 50 ohms for R3 in the R3 row? You got to make sure these values are put in the correct cells. Otherwise, things get really wonky on you. The total was the formula where we add these guys together and we have 450 ohms. 9 volts was given as a source. What would be your next step? According to our friend Ohm's law, V, I, and R, and the only other formula we're going to use is the first power pie chart, P, I, V. Those are the only ones we're really going to use for the bulk of our work. So what was hip about Ohm's law? Ohm's law said, as long as you have two quantities, you can calculate a third. Take a look at the first row. Do I have two quantities? Nope. Second row? Nope. Third row? Nope. Fourth row? Hey, I've got two quantities. I can calculate a third quantity using Ohm's law. What is my missing quantity? My missing quantity is under what column? I. I stands for what? Current. Take a look at Ohm's law circle. According to this circle, if I'm looking for current, I take my finger and I put it over the eye. Is my finger over the eye? Is your finger over your eye on your circle formula if you've written it down? You shouldn't just be watching, you should be doing, okay? Actively doing this. So I'm giving you time to do this, and I say to do this, you should be doing this. So you put your finger over the I. What's left in the circle formula? V divided by R. Do you have a V? Do you have an R? Woo-hoo. Take 9, divide by 450. And so when you go to do this, 9, calculator, 9, divide by 450, you end up with this scientific notation display, 10 power negative 2. Is this engineering notation, yes or no? The answer is no. Engineering notation says we have to have powers in multiples of what? Multiples of 3. Is there a magic button on this calculator that can quickly change this scientific notation answer into engineering? Guess what? It is your engineering key. If I press engineering, right there, voila, it automatically converts to the appropriate 10 power of some multiple of 3, and the value is given as proper engineering. So this works out to be 20 times 10 power of negative 3. According to our chart, going back to here, go back to the share for 10 power negative 3, right here, is thousandth. What is my engineering prefix? It's pronounced as milli. What is the symbol for milli? Lowercase m. So the 10 power negative 3, and this chart should be in your notebook after today, 10 power negative 3 is pronounced as milli, and the symbol is lowercase m. That means, my friends, on this sheet and my calculator, I'm going to write this in as 20 lowercase m, capital A. That works out to be 20 milliamps. Everybody say that. 20 milliamps. 20 milliamps. Okay? So 9 divided by 450 gave you some odd decimal number. You hit the engineering key, and voila, it gives you 10 power negative 3. Are we good with that so far? Whew. Now, we've solved that row because there happened to be 2 quantities that gave us a third. Can we do anything? What else would we do? What would be a plausible next step? We need 2 quantities in order to solve for a third. It doesn't look like we've got 2 quantities in any of the other rows. So we need to go back to a concept in series circuits.
Burden is constant.
Yes. What is the same through all parts of a series circuit?
Like, call me or you?
Right here. Let me go back to this share real quick and go to here and do share in a previous slide. Yes. If you go back to this previous slide, current is the same throughout a series circuit. In a series circuit, current's the same. As I said, the current between the first and the second resistor is the same, between the second and the third resistor is the same, current at the bottom wire is the same. They're all the same in a series circuit. If you look at the formula, IR1 equals IR2 equals IR total. They're all the same. So if you, what this means in a series circuit, if you find one, you have found them all, okay? If you find one, you have found them all. Before you go jamming that 20 milliamps in here, and you fill this column in with 20 milliamps, what should you do? You want to double check this. If you made a mistake and you miscalculated this number and you filled in the entire column, there goes the whole paper, half the paper. So you may want to double check that. So it only takes a moment. You clear your calculator, take 9, divide by 450 equals, hit your engineering key, and yes, it does say 20 with a power of negative 3. That's 20 milli. You're feeling really confident about that now because you've double checked it. Now, and only after all of this effort, can you confidently fill in Yep, I got 20 milliamps there. I got 20 milliamps there. And I got 20 milliamps there because this is a series circuit. Woohoo! We're getting there. There were 16 squares total. We got more than half of them done. What would be the next thing that you do? Hold power for last. Save power for the last. Can we solve for V on that first row? How do I find V on that first row? Do I have two quantities that will allow me to calculate for V? Well, according to Ohm's law, V is at the top of the circle. What do? I cover the V with my finger. So V would be equal to what relationship of these quantities left? I times R. Do I have an I? Do I have an R? Yes. And so, do we still have 20 milli in your calculator? Yes. Can we just multiply that right now times 100? Boom. That calculates to be how many volts? 2 volts. 2 volts. It's interesting. We calculated that voltage earlier using voltage divider formula. Now we're recalculating the same value using Ohm's law. So that V is equal to this I times these ohms. Now, how do you key this in? Let's suppose, hey, Co, I cleared my calculator. I no longer have 20 milliamps on my display. How do I do the next one? I need 20 milliamps times the 300. That's really easy to do on your calculators. Watch this, okay? It is 20. How do you express milli on your calculator? You have a button here called EXP. EXP is your 10 power key. Some of your calculators are shown 10 power of X. So if I touch this, it shows me the exponent that I'm going to key in. Milli was some multiple of 3. Milli is what multiple of 3? What exponent of 3 is a milli? Who remembers?
-3.
It's a -3. Now on your calculator, how do you key in milli? The negative, you don't use the subtract key. Right over here, you see this negative in parentheses? You find this key, -3. Now what I've keyed into the display of the calculator is 20 milli. Now I'm going to multiply by 300. Enter. How many volts does that calculate to be? Wow, 6 volts. Didn't we calculate 6 volts earlier using voltage divider formula? Yeah, we're verifying it right now, right here. So 6 volts is equal to 20 milli times the 300 ohms. Woohoo! And the last one here, let's calculate 20 milli times 50 ohms. So I will clear, and again, I will do this as 20 milli is some power of 10, -10, -3, so exponent -3. So right there's my 20 milli. And I'm now going to multiply this by 50 ohms and hit enter. And I end up with how many volts? 1 volt. We did this earlier with voltage divider formula. And guess what? Do these 3 voltages in green add up to be the total? The 2 plus the 6 plus the 1 adds up here. We're really happy right now. We're rocking. How do I calculate this thing called power? This is also pretty easy. If you look at the very first power symbol, P, if I put my thumb over the P, what's left in my circle formula? The relationship is I times V. So P is equal to I times V. Do I have an I? Do I have a V? This works out to be my 20 milliamps times 2. So again, on my calculator, clear. How do I key in 20 milli? 20 exponent -3. There's my 20 milli. And I'm going to multiply this by my voltage of 2 volts equals. I end up with some scientific thing. I know that's not engineering because the power of 10 is some 10 power of -2. That won't work for me. So I need the engineering function to hit engineering. Guess what? This works out to be 40 exponent -3. So this is 40 milli something. Power is measured in what units, my friends?
Watts.
Watts. So this would be written as 40 milli with a capital W, lowercase m, capital W. That's 40 milliwatts. We're going to do the next one. So I'm going to clear 20 exponent negative 3. So there's my 20 milli again. Now I'm going to multiply this by the V of 6 volts. 6 equals. End up with something other than engineering. So I have to tap my engineering key. How many, what number do I have here? 120, again, exponent negative 3. So this would be 120, what?
Milliwatts.
Milliwatts. So far, so good. We have one more resistor to do. So 20 exponent negative 3. A repetitive function is a really nice practice. And we're going to multiply this by 1 volt. Again, I don't end up with a multiple of 3 for my exponent, so I want to hit engineering. And this tells me how many watts I have. So 20 exponent negative 3 would be 20 milliwatts. Are we good with that so far? Okay, here's the magic square or magic cell. If I use Watt's law, if I want P total is equal to I total times V total. Take this I times this V, multiply these two, and I should get a power total. So 20 exponent negative 3. And I'm going to multiply this by the 9 volts. I'm going to end up with, again, I have to hit my engineering key. How many milliwatts? According to this, 180 milliwatts. So I did a diagonal here because through Watt's law, I calculate 180 milliwatts. But we should recall, for series circuits, we should recall for just a moment, let me go back to the share screen. I gave you a power formula for series circuits. And according to this power formula for series circuits, what's it say for total power? Isn't total power equal to the heat of the first resistor plus the heat dissipated by the second resistor plus the heat dissipated by the third? In other words, if I add the powers, I will get total power, according to this formula on this part of our PowerPoint. I'm going to come back to my camera. Well, guess what? Over here, if I add this power, 40 milliwatts plus the 120 milliwatts plus the 80 milliwatts, guess what I end up with? If I add them, I also end up with 180 milliwatts. Could I use that as a double check to my math of Watt's law? The first 180 milliwatts was calculated using the Watt's law circle formula. The second 180 milliwatts was calculated using the formula off of my series circuit PowerPoint page. Are we good with these numbers? Is this a good practice for you? Because it is actually given to you on this particular slide, which I blanked for a moment. Right here. Covered it up in green. So if I grab the screen and I remove it now, bam! Are these the same numbers we calculated together, my friends?
Yes.
Current was 20 milliamps. The entire column is all the same. The voltages we calculated 2 different ways. We recently calculated using Ohm's law. We previously calculated these same voltages using voltage divider formula. The powers through the very first power formula, PIV, all of these were individually calculated. Do they add up to be the 180 milliwatts? Yes. Bingo. I love the VIRP chart. We call this the VIRP chart, V-I-R-P. And so when we do our analyses for our circuit builds, you will be using this method. Create a simple chart, columns and rows identical to what we've done, and then use your circle formulas, fill things in, but you always start with your freebies. Any questions on this so far? Next, digital multimeter. Okay. Here's a few of the digital multimeters I happen to have in my collection. Too many. And if you're looking for the one that I asked you to buy in Amazon, it ain't here because I don't need another calculator. I got more calculators I know what to do with. Let's go ahead. If you would, I need to give you, can we take a quick 5-minute break? Is everybody okay with that? Take 5. I'm going to time us for 5. Time us for 5.
Hey, what kind of meter is that white one?
The light colored one here happens to be a fluke. It's a very old fluke standing next to the yellow next to it, which is also a fluke. So one is like 30 plus years old and then the other one is current. But they're both manufactured by Fluke, which is one of the best names in the industry. All digital multimeters should work reasonably well. You can get the multimeter that I specified in your syllabus is an excellent multimeter for the price. Are there more expensive multimeters? Yes. Do they do anything more? Some more, but not a whole lot more. Are they all accurate enough for the work that we're going to do together? The answer is yes. So no. This yellow one here, there's no reason for you to spend $180 for this multimeter. There just is no reason for you to spend $180 for this multimeter. This yellow one here, the Fluke. Hopefully that answers your question.
No, it looks pretty cool because I have a Fluke 87. I think it's 87 for
yes,
work.
Yes, very nice. Yeah,
It kind of looks similar to a far right one. But I got it for $20, which is hecka cool.
Yeah, you got a steal deal there because retail on the market, if you buy that from direct resources, is going to be way more than $20.
Yeah, I think when I checked at the time was like $600, something like that.
It's a couple $100 for sure for any of the Flukes.
Mm-hmm.
It is the standard of the industry. It gives you bragging rights, and a Fluke meter is kind of like, you know, the Porsche of or the Ferrari of multimeters. You know, it's just, you are paying for a brand name, yes you are, but you also are getting one incredible instrument that will last you forever. So this light colored one that I have here actually goes back to I want to say 80 something, 83.
Still works too?
Yeah, so 16.
That's awesome.
Yeah, we're 30 years old, this thing. Probably older than one or the couple of your parents. And it works just fine. built like a tank. Good stuff. But this is an interesting picture because it also shows, if you look at it very closely, it also shows the circuits that you're going to be building for this circuit F and circuit G. Circuit F and circuit G. Woohoo! Fun circuits.
Should I get out my breadboard now? Are we going to be working with that?
Yeah, we will. Yeah, we will.
Should I get it set up then?
Yes, get your breadboard ready, get your resistors ready. You want to pull out the 100 ohm resistor, and you pull out the, where's my meter? I think I wanted the 330, the 100 and the 330, yes. So whoever's still on the 2 minutes left of our break, get your breadboards ready. Get the 100 ohm resistor pack, the 330 ohm resistor pack, and your jumper wires ready to build. You're also going to need the switch from your kit. For those of you who don't have the exact kit, in place of a switch, you can have a jumper wire. So yeah, while I happen to have you on, okay, that's the end of our 5 minutes. Our 5 minutes is up. If you ain't back by now, too bad. I'd like to ask permission, if I may. Kirsten is one, and Anna Lee. Anna Lee, are you there, dear?
Yeah, I'm here.
Do I have both of your permissions to show your circuit builds to everybody? If you're shy, it's okay.
Sure.
Okay, that's great. Kirsten, are you okay with that?
Yeah.
Okay. Let me do this. Let me do this. The thing about the selfie is I need to validate that the circuit build is in fact yours, and having a piece of your face in there was a good way of showing that. But sometimes because of lighting, because of angles, that selfie is really tough to get. So I was asked, is it okay if we use some form of ID in the picture? That is you. So your school ID, hey, it's you. It's got your name, it's got your picture, and boom, you lay it on top of your circuit board. That is as good as a selfie, okay? If I can get a piece of your smiling face, all the better. The first one with the card, yes, because it was a single LED. It was so bright and washed out everything else. It was hard to get the selfie in for some of you. Here's one, okay, like this, circuit, all good. And then here not, so we have the ID in there, and that works out just fine, okay? So I wanted to show that to you, that yes, if you couldn't get your face in there, then some piece of your ID would be great. Here's Anna's, and Anna's using slightly different, a little larger board. She happened to have had this from before, and she's powering off of a Raspberry Pi project, which is another great way of doing this. This works really, really well. And she's got good lighting in the room. The key is to try to get good lighting in the room. So as long as you can get good lighting in the room, you can take the picture, we can see your smiling face or some part of your face in there, and the circuit builds, and boom. You know, everything is very clear from this angle. If you hold the board flat on the table and you take it parallel to the table, I'm not seeing all the wires as clearly. This is a really good way of showing it. And yeah, good lighting. Okay, so when you have good lighting, it makes the circuits very easy for me to see what the wire path is. Very important I'm able to see the wire path in order to know that things are built as they should be, like here. And again, if the selfie wasn't possible, then a piece of ID, you know, your school ID or something, you just cover up the parts that you want to keep private. But yeah, this works. So I just wanted to show that to you for circuit building alternatives. And yes, if you don't use the pre-cut, pre-bent ones, it's perfectly okay to have your jumper wires jumping all over the place. I believe, was this one done this way? Yeah, Erica, oops. Let me ask your permission first. Erica, can I show your pictures as well, please?
Yeah, sure.
Okay, thank you. This is another great way of doing this. And if you look at Erica's right here, you can see that she is not using the flat laydown wires, but using the ones with the steel pins. And if you follow the circuit path on this, this works perfectly fine. So from the positive rail, we have a blue wire, goes to a wire to the LED, LED wire makes a connection to the resistor, resistor makes a connection over to here to this blue wire, the blue jumper jumps over to the negative rail, boom, it's a complete circuit. I can see everything. So it does not have to be with your pre-cut, pre-bent wires. But as the circuits become more complex, you'll find if you do use the pre-cut, pre-bent wires, your circuit builds will be less, they'll take up less space and will be easier to troubleshoot. But this is perfectly legal. And as long as I can see this amount of detail, I can do the wire trace path and see clearly this is circuit E. I've got a series parallel arrangement. Here's the series resistor, series LED, and then these last two are in parallel with each other. This works fine, okay? So it does not have to be with pre-cut, pre-bent wires. So I wanted to show you all this. And if you can't do a selfie, then some form of ID in the picture will also work. Okay, Digital multimeter. When we use the DMM to measure voltage, it is referred to as a what? Voltmeter. When we use the device to measure current, it is referred to as a what? Ammeter. When we use it to measure resistance, it is referred to as a what? Ohm meter. And I'll highlight those in yellow. Those are words that are very specific, point to very specific functions. Next, when you're making voltage connections, all of these have to be followed to the letter. So I have 3 slides I'm going to show you next. One is for voltmeter connections, ammeter connections, ohm meter connections. Very, very specific. You also have in your reading assignment, online reading assignment, things that will guide you to essentially the same information. So you will be reading these in detail, and I will follow up on Thursday for those people who are going to be, well, hopefully all of you, except for 1 or 2 that were Tuesday only people, but the rest of you will follow up on Thursday for some follow-up questions. I really want to get into building that circuit. So I will leave this. I've got one more formula to pop in here, a current divider formula, and then I will post this in Canvas this evening, so you will have this as a resource later on this evening. So within half an hour after we close, you will have this PowerPoint in detail so for you to follow through in your follow-up reading. So let me stop the share, and we will go to camera. So stop share. Good. Go to my camera. Good. Now get a board. Here is DOS board. And I don't need calculator for this, but I do need a few things. So I'm going to grab me my power supply. The power supply will go that part of the board like that. And I'm going to grab me my resistors. So I will take my bag and let's do this. Focus is important. All right. Get my 330 ohm resistor bag. Get my resistors. And I will snip out a 330 ohm resistor. There's my 330 ohm resistor. I will get my needle nose pliers. Oh, one of your classmates reminded me a really good resource for needle nose pliers that are really like jewelers pliers that are really inexpensive. Our friends at Harbor Freight. Harbor Freight's a wonderful resource. So what I've done is I've taken the resistor, cut it, bent it, and this is my 330 ohm resistor, which I'm going to mount on the board somewhere. So I'm going to mount it here. There's my 330 ohm resistor. I am going to get some jumper wires. So I'm going to grab me jumper wire from here to here. Grab me a jumper wire. I'm going to connect the yellow jumper wire to the side of the resistor.
Are we building the same circuit too?
Yes, you are.
What pins are you putting those in? Or that really doesn't matter, huh?
No, it doesn't matter as long as I have yellow connected to the left side of this resistor. So where it ends up on the board is not critical.
Okay.
So close this, because again, never leave this open, because you knock this over, you're going to have a whole lot of tears. So we're done with the 330 ohm resistor. Put it away, zip it back up. And then from the 100 ohm, since we used several of these last week, we should have in here from last week left some 100 ohm resistor that we've pre-cut and pre-bent before. And I'm going to take this guy and mount it onto the breadboard. right here, right here. So I now have 100 connected to a yellow jumper, connected to 330 ohm resistor. So far, so good. I am going to get from my kit a switch. So from my box of parts, very carefully open this up. Very carefully grab a push button switch. Let's push button switch, close, lock. Make sure these are locked in place so they don't open and spill out all over the place. I have a switch. And the switch, if you look at very carefully, happens to be set up like this, if you will. And it turns out that the spacing between these is that 2 tines will go above your dip support groove, and 2 of these tines will go below your dip support groove. So here, this will be very specific. I'm going to mount this guy, and I'm going to bring this down really, really close onto the board for you in a moment. I want, let me focus on here. There we go. What I need is to have one of the tines of this switch connected with this side of the 330 ohm resistor. So one tine of that switch is connected to the same set of tie points as the 330 ohm resistor. It doesn't matter what number row, just make sure that wherever this 330 ohm resistor ends on the right-hand side of the circuit, it is connected to one of the tines of the switch. If you're happy with that, now push that switch in place onto the board, and so it should sit onto the board this way. It straddles your dip support groove. So 2 sets of tines are on this side, 2 sets of tines are on this side, and you simply push it flat onto the board. Are we good with those 3 components so far? We have a resistor, 100 ohm, to a jumper, to a 330 ohm, to this upper right tine of the switch. Next, I'm going to grab an LED. Any LED will work.
I have a quick question.
Please go right ahead.
Is it okay if we slightly extend if they don't quite fit over the dip?
If it doesn't quite fit over groove, turn it 90 degrees because you might have it 90 degrees off. In other words, the little switch.
Oh, never mind. I was just being too gentle.
Yes, okay. Yeah, the little switch, if you look at the back side of the switch, you'll notice that the spacing, if you look at the back side of the switch, you'll notice that the spacing between these tines, these pins, are not equidistant. You have a pair closer to each other, a pair closer to each other, but this pair and this pair are farther apart. So the groove sits between right here. So this pair that's closer together is on one side of your dip support groove. This pair of pins that's closer together sits on the other side of your dip support groove. And that's how it goes onto the board. Don't turn it 90 degrees and force it this way. If you try to straddle the groove this way, you'll end up breaking the switch. Rotate it so that you have this orientation, and the pins that are closer together will go on one side of the dip support groove. The other pins that are closer together, as shown here, will go on the other side of the dip support groove, and it ends up on your board like this. Okay, and yes, you do give it a nice firm there, push it down, and it will go onto your circuit board just fine. Now, LED. The LED, remember, lead is positive, short lead is negative. Give them a tiny bit of splaying apart, not a whole lot, just some. The long lead is positive and the short lead is negative. So you want the long lead to connect to the switch. So let me focus back onto here. And let me bring this way down. Maybe this will help us out. And focus again on the board. Ta-da. All right. Here's the long lead of the LED. And the long lead of the LED will go onto a set of tie points that is like that, if you will. Okay? So the long lead of the LED is here, connected to the lower left pin of the switch. The upper right pin of the switch is connected to the resistor. The lower left pin is connected to the LED. So far, so good. Okay. Then the only thing left to do is 2 more jumper wires for the power rail. So I'm going to grab this side of the circuit. Will go to ground. And 1 more jumper, positive side for power. This will go at the top. There. So what I've got going on, my friends, is positive rail from my 5-volt source, red line to a set of tie points to my first resistor, 100 ohms. Second resistor is connected to the first resistor with a jumper wire. And then the end of the second resistor is here. It's connected to my switch at the upper right-hand pin. The lower left-hand pin on the other side of the dip groove is connected to my LED, long lead. The short lead of my LED is the negative side, which is connected to a last jumper to my negative side of my source, which is my blue rail. So everybody okay with how this guy is set up? Now, the moment of truth. And the moment of truth is we're going to connect this to power. And as I connect this to power, remember, hold the power supply down, then make your connections with the USB cable. Then you can turn on the power switch. You know that the LED, the green LED is lit, showing you that it is on. LED off means the circuit's off. So the power supply is now lit. Now, to check the circuit for its functionality, if I touch this button now, does my blue light light up? Yes, it does. That means I have continuity, yes? I have continuity from the positive rail through the 2 resistors, all the way through the switch, through the LED. And the LED is here only to let us know that, yes, the circuit is built properly, okay? Once the circuit is verified to be built properly, we want to remove the LED. I can remove the LED, and I can put in a short jumper wire where the LED was, and a short jumper wire where the LED was, right there, and that completes my circuit. Now, several things. Is there any questions as to how this guy is built? It's only 2 resistors, a switch, and this red jumper now takes the place of where my LED was, because the LED, I don't need it for my actual measurements. So far, so good. All right, we're going to do a very quick analysis of this guy. Here. I'm going to power this guy off, set it aside for a moment, bring my camera back up. I need something to focus on. So here, focus. Okay, cool. All right. What we have, my friends, is this. We have a source, 5 volts. You have two resistors. I'm going to label this point A, B, and C. This is R1, this is R2, 100 ohms. 330 ohms. Pardon me. I'm not going to draw on the switch because when the switch is closed, I have a complete circuit. Pardon me. Okay, I'm going to draw V, I, R, P, VIRP. There's only an R1, an R2, totals. A column, a column, a column, and a column. So if you're not done with the circuit building, not to worry, but we can do this analysis together, okay? Oops, I just smudged the heck out of my paper. Sorry. So what did we say earlier when we were solving for our VIRP charts? What was the very first thing we ought to do? We got 3 rows, 4 columns, there's 12 cells to answer for this exercise. We're going to do some calculations, won't be hard, but we're going to do some calculations. What's the first thing we ought to do to start filling in these 12 cells?
Put in the givens.
Put in your givens. What are we given?
R1 and R2.
R1 and R2. R1 is how many ohms?
100.
Where in this chart do I write the 100 ohms?
R1R.
R1.
In the R column, in the R1 row, yes? So like bingo, it's going to be this cell. I'm going to have 100 ohms here, yes? And by the same token, R2 should be in the R2 cell row, so it should be in this cell, 330 ohms. So are your 2 resistors, the freebies, the 2 givens, filled in already? So far, so good. What else is given that we can fill in?
The voltage.
Voltage source is 5 volts. And where does that go in the grand scheme of things?
Totals under volts.
Totals under volts. So this cell here, 5 volts. So far, so good. Well, those are the givens. Now remember, according to Ohm's law, tearing the paper apart, sorry, V, I, and R, and then P, I, and V. According to Ohm's law, I need 2 quantities in order to calculate a third. What do I have? I don't have any 2 quantities on the first row or second row or third row. Lord, where do I start? I can't use Ohm's law yet. What can I do? What do I know? What do I remember about a series circuit?
Total ohms?
Total ohms. Is there a way of determining total ohms in a series circuit? How do I find total ohms in a series circuit?
You just add them all.
Add them.
Come up. We did that earlier, yes? I have 100 plus 330 gives me a total of 430. What are my units? Ohms, yes? 430 ohms. Is everybody okay with that so far? Now, what would be my next step?
Total amps?
Likely, we want to use these 2 quantities to calculate the third. Before you jump into that, this happens to be a simple 2 resistor circuit. Some circuits may have a lot more resistors. When you're presented with a bunch of resistors, you should double check this total, make sure you're good with this. So 100 plus 330, are we good with the 430 there? Are we confident that total adds up to 430? Because what happens if this number is written incorrectly? Everything else will be wrong. Are we happy with this? If we're happy with this, then we can move forward with calculating current.
Very happy.
So if we're looking for current, I, and I have a V and an R, can I use this circle formula, cover the I, and if I cover the I, what's left in my circle? V divided by R, yes? Do I have a V? Do I have an R? Can I take the V and divide by this R of 430? Yeah. let's go ahead, grab our handy dandy calculator, and take 5 divided by 430, and we end up with some kind of a power of 10 other than some engineering. So you have to hit engineering key, and this works out to be this number with a 10 power negative 3. So 10 power negative 3 was what prefix? We did this earlier.
Milliamps.
Would be in milliamps. So milliamps. Now, what were our rules of rounding? The first 2 digits in front of the decimal point are clearly 11. What are our next 2 digits going to be according to our rounding rules?
0.63.
It would be 0.63, okay? Because you always look at the third digit after the decimal point. The third digit after the decimal point, if it's 5 and up, we will round up that digit here, the second digit, incremented by 1. So the 0.627 works out to be 0.63 on our answer sheet. So far, so good? I would recommend, before we fill in this column, we should double check our calculations. So 5, again, divide by 430 equals, hit your engineering key, you have 11.63, 10 power negative 3 is in fact milliamps. Are you happy with this that we've written down as being the current? Because you've calculated it twice, yes? If you're happy, what can you do next? In a series circuit, what is the same?
Current is constant.
Current is constant throughout a series circuit, correct. So you can now fill this in with confidence. 11.63 milliamps.
I think Efren asked the question. We typed it.
And question is, why don't we use significant figures? We're using rounding rule to this class. Yeah, our standard will be to round to the 100th. That will be our standard throughout the program. Any class that you are with me from here till you get your certificate of achievement in this discipline or that discipline, and ultimately as you get your degree in electronics tech, we will be rounding to the standard of 2 digits after the decimal point. So if the ground rule is set and our standard is to round to this number of digits after the decimal point, then that's what we're looking for, okay? So if there's any vagueness, let there be no vagueness. That is our standard. We will uphold that. Hopefully that answers Ephraim's questions. Okay, cool. Next, that being said, all right, what do we do next? What would be the next thing we could do based on Ohm's law?
Find volts for R1 and R2.
Yeah, and according to the circle formula, if I cover up the V with my thumb, what's left? V would be equal to some relationship between I and R. What is that math relationship supposed to be? It's supposed to be multiplication.
Multiply.
So do I have an I? Do I have an ohms? Well, all right. Unless you happen to have, and we're not going to talk about using calculator memories for this exercise. We're just going to use your rounded off answer. We'll all be consistent in using the rounded off answer for now. We clear our calculator. I need to key 11.63 milliamps, and I'm going to multiply it by 100 in order to calculate voltage. How do I key that into my scientific calculator? I clear. I will key in 11.
You can check in here, babe. I've got my mic muted.
Okay. I'm going to take the 11.63, and how do I key in milli? It was the EXP key, 10 power key. Milli is not 3, but it is -3. How do I key in negative? I use the change sign key, 3. Now I have 11.63 milli. Now I'm going to multiply this by the 100. Bam. And I end up with a multiple of 3. Good. This is a 0, 0. So that means these are whole units. So I will write down 1 point. So what are my next 2 digits going to be?
16
1/6. What are my units going to be?
volts.
I use V for volts. Very good. Is everybody okay with that exercise so far?
Yeah.
Cool. Clear. We'll do it again for the next one. So 11.63 exponent -3. Get really good with 2 fingers here, 2 hands. We're going to multiply this by 330 equals. Again, the 10 power will be 0, 0. So these are whole units. So it's 3 point what? 3 point. If you look at this, 837, this third digit is a 7, so it's greater than 5. What should we do with that 3? Round it up to 4. So you are correct. You are all correct. This will be 3.84 volts. Wow. And if we double check this, if we add these two together, do they in fact add up to 5 volts? Cool. Outstanding. We'll hold off on calculating the power because we're not going to measure power. You can calculate power on your own. What I would like to do is let's verify this using measurements. We're going to use our digital multimeter. All right. So I have the circuit built. Here's the circuit built. And I'm going to hook it up to power. So the circuit's hooked up to power. I'm going to energize my power supply. Power supply is energized. Now, the best way, best way to make measurements, since these guys are cut down really, really low and it's hard for us to get in here, my recommendation is let's go ahead and use a pair of these pre-terminated pin jumpers. And we're going to use these in conjunction with your multimeter. And your multimeter will be, where did I set my multimeter? Lord, here it is. Multimeter will be with alligators. So I can use this probe and I can go to here, or I can do it this way. I want to verify the measurement of voltage on the first resistor. I can do it this way. Hook this guy up here. Hook this guy up here. And we expect much. We expect 1.16 volts. Let me raise this up a little bit further so we can have a better view. Refocus. It is now refocused. Change my angle of light and turn the meter on for DC voltage. We expected 1.16 volts. If I energize the circuit by pushing the switch, do I have something close to 1.16 volts? I do. And when we go to do a voltmeter measurement, we don't round this one off. We write down all the digits of a voltmeter measurement. So this is 1.154 according to my machine. So I'm going to write this above here, 1.154 volts, M, meaning measured. Does that compare reasonably well with my 1.16 volts? Sure does. Now, if I choose not to use the alligators and I choose not to use the pins, suppose for a moment you happen to have standard probes, and I'll show you how to do this with standard probes. I can have a set here somewhere. Standard probes, standard probes. Yeah, here's a pair of standard probes. All right, black goes to common, red goes to V. And with standard probes, you're going to use the stabbing technique. And the stabbing technique means very simply this. You're going to stab the red probe right to the end of the wire where it attaches to the board. So I'm just stabbing right down on there. And I'm going to get this probe and I'm going to stab on this side of the resistor and hit the switch. When I hit the switch, I end up with 1.153. This pretty much what I had a moment ago, 1.154, 1.154. Fluctuates between 3 and 4. Is this basically the same? And the reason why there's a slight fluctuation is because even with the stabbing technique, I'm pushing down fairly hard where the resistor goes into the board, because the amount of pressure slightly varies between my two hands. This last digit is fluctuating slightly. And that's because I'm using the stabbing technique. Try not to use this by touching the two this way. You can still get a reading. I'm going to do this. Since I can't, I'm going to make a switch close by putting in a jumper wire, and that'll just close my switch. There, now my switch is closed without me having to push it. Now, if I go here to here, and I just touch here to here, I will have my 1.53, 1.54 volts. Now, suppose I switch the polarity of my leads. Right now, the red lead is on the positive side of that resistor, and the black lead is on the negative side of the resistor. Why is the red lead on the positive side? Why is that left side called the positive side of the resistor? Because the left side of R1 is, in fact, connected to the positive rail. So as it's connected to the positive rail, this side of R1 is positive, and the right side is negative. So when I do this, my digital multimeter shows 1.54. Now suppose I flip the leads around. Watch this. If I flip the leads around and I go to measure this way, same magnitude, but do you see on the display on my multimeter, do you see a negative symbol? I have a negative 1.153 or 1.154. And the reason why it's negative is this. The red probe is what senses the polarity when we pull it towards the black probe. Did you hear that? The polarity of what we measure is totally dependent on what color probe? The red probe. When we reference to the position of the black probe. So right now, if I put my red probe on the right side of the first resistor and my black probe on the left side of the first resistor, the red probe will see the negative side of that resistor, which is why the voltage is negative 1.153. Okay, so far so good. What did we calculate for the voltage for R2? 3.84. Well, if I put my red probe here and my black probe here, measure, guess what? I got 3.84 right on the button, yes? Isn't that nice? If I do this, I reverse my leads, put the black probe here and the red probe here, voila, I end up with a negative 3.84. Negative doesn't mean it's wrong. Negative simply means my red probe is seeing what side of that resistor. It's seeing the negative side of that resistor. So if you measure a negative value, doesn't mean it's wrong. It just means the red probe sees the negative side of that device. Do we have any questions on this so far? So we verified VR1, we verified VR2. I want to write down the value that we verified for VR2, and that was 3.84 volts. And I want to verify the source, meaning I should verify across both resistors. And if I hook up between both resistors, from the beginning of the circuit to the end of the circuit, do I have my full 5 volts according to my digital multimeter? And is that positive? Yes, because I have the red probe on the positive side of the two resistors, black probe on the negative side of the two resistors. Suppose I have my probes around. If I flip my probes around, woohoo, it's a negative 5 volts. So far, so good. So everybody okay with the voltage measurement so far? All right. Now, to measure your resistors, to make sure your resistors are correct, turn off the power supply, disconnect the USB. Actually, you can either remove the power supply, or what you ought to do is move the connection. I remove the jumper wire at the bottom of the circuit. Now there's no physical connection of this circuit to the power supply, even though it's de-energized, even though the power is disconnected, it's physically still on the board. And if it's on the board between the red rail and the blue rail, it will still affect our measurements for resistance. So I pull out this jumper wire, so there is no physical connection now that completes a circuit from the positive side to the negative side. These resistors are hanging by their lonesome. I'm going to switch my multimeter to the ohm position, and I want to verify the ohms of my first resistor. It's supposed to be 100 ohms. Do I have 100 ohms? 99.1. That's pretty good. Suppose I flip the leads around, change the polarity, and measure. 99 point, yeah, I'm moving the board. 99.1. Notice there's no positive or negative when you're measuring resistance. There is no polarity when you're measuring resistance. It's solely a magnitude, okay? And suppose I measure the resistance of the 330. Should be pretty close to 330. Let's see where this ends. 329.6. 329.3. And again, it changes slightly only because the amount of pressure that I'm putting on differs from one hand to the other, and I'm not pushing to the point where I'm going to break my pins, okay? But I verify I'm pretty much there. What were our total ohms? 430. If I measure between here and here, do I have something close to the total? And the answer is, I wanted 430. Oh, this is very interesting. Look at the display of this multimeter, and it's hard for you to see, but in this lower right-hand corner, is going to be either a K for kilo ohm or an M for mega ohm. And you can kind of see it if I get it off of the, too much glare here, sorry. Raise this up, change the angle, go to this side, and measure here to here. And do you see the kilo ohm symbol in the lower right-hand corner? It gives you 0.427 kilo. Is my display in proper engineering notation? 0.27 kilo. It is not in proper engineering notation. It is in engineering notation because I see kilo, but this is not proper engineering notation because I get a decimal point in here. So 0.427 K. If I key that into my calculator, 0.42, turn it on, Co, 0.427 kilo would be exponent 3. 0.427 exponent 3 is kilo. The moment I hit enter, it'll give me some scientific. I hit engineering. Isn't that 427 ohms? Pretty close to my 430. So what I mean to show you is 0.427 K is the same as 427 ohms. Are we okay with voltage and resistance measurements? Do not. What did I say? Do not. Do not attempt to measure current this go around, okay? Do not attempt to measure current. I need to have a discussion with you all about measuring current. So if you try to measure current without my discussions, you're off on your own, and if you end up burning out a fuse on your digital multimeter, then you will suffer the consequences of having to replace said fuse. And the fuse in your digital multimeter, should you ever need to replace it, here's one that's opened up. Happens to be there's two fuses in a digital multimeter, and one of them is a main fuse and one of them is a current meter fuse. And if you happen to burn out the current meter fuse because you didn't follow my directions by not measuring current until you're told to do so, replacing that fuse is not hard. The cost of that fuse is not high. The fuse is maybe a 25-cent fuse. Replacing it is as easy as using a tool, lifting up one end, pulling it out, and there's the fuse. Replacing the fuse is as easy as putting it in like so. Did that take a whole lot of effort? No. But here's the cost of replacing the fuse. The cost of replacing the fuse is You have to go out and buy that thing. Where are you going to get it from? There is no more Radio Shack. You can't just go to the hardware store and buy this from a hardware store. You have to special order that guy. So you got to send out for it. You got to wait for it to come. Then you receive it. Then you got to take the screws off of the back of this thing, open this guy up, find the appropriate fuse, pop it out, put in the appropriate fuse, close the thing back up, and hope that everything works. So is anybody going to try to measure current before I teach you how? Hopefully not, because then you'll have to replace your fuse if you end up blowing it out. Everybody okay with the circuit build?
I have a question.
Yes, please.
If you blow out your ammeter fuse, can you replace it with the voltmeter fuse? Like, can you just
Nope.
No. Oh, okay. They have to both be in there.
They both have to be in there. The DMM fuse is a fuse for the entire device. The ammeter fuse,
okay.
yeah.
I misheard.
So that's got to be there. So that it's not a spare fuse, okay? The ammeter fuse is specifically there to protect the circuitry from accidentally burning out the circuitry, so you burn out a fuse. And you can very easily burn out the fuse if you don't follow my directions on how to make the measurements, which I will defer for now. Don't make any current measurements. So only measure voltage, only measure ohms. So when you measure ohms, you have to make sure that the circuit not only is deactivated, unpowered, but also physically disconnected. Notice that last jumper to the negative rail has been physically removed. That's the only way you're going to measure resistance, is when the circuit is de-energized and not connected to a power source. Okay? Otherwise, voltages, you just remember using the appropriate polarities. Yeah, and we'll talk more about this and many other things come Thursday. On your what to do between now and Thursday is this. I will go to somewhere here is a yes, no, yes, no. Go here. Aha, cool. Dashboard, cool. I'm going to go to Canvas, and I'd like for you to just look at my screen. All right, so several things you can do between now and Thursday. I happen to have in here, I will put in here our PowerPoint. Notice that it doesn't have a green dot, so I haven't activated it yet. But you have online assignments with directions and a sign-off sheet. This is worth how many points? 120 points. Get going on this. And what these are, my friends, is, first of all, you have a sign-off sheet. This is an Excel document. And the Excel document goes to show URL, that's my URL, paste it in here and go. If some of you, when you go to play any of these links, if it doesn't come up, if there's any kind of an error in this loading, this happens to be a flash error. You come up to this little lock symbol. There's a padlock on your address bar. Here's your address bar. There's a little padlock. You click on the padlock and you want to make sure flash is not blocked. You want to make sure flash is allowed. Flash and pop-ups, you want to make sure flash and pop-ups are both allowed. And as long as it's allowed on your address bar by clicking this little padlock, then you will be able to see any and all videos associated with any of these lessons. This one is voltmeter circuit connections. It's a great lesson. And it basically reiterates what we had talked about briefly, but this gives you more detail. So you'll go through each of these links, and when you complete any one, so here's the first one, when you complete any one, you put a date in here. So 6-23-2020, boom, you have a date in here. When you complete the next one, put in the next date. You have all the way till Sunday night to complete this. It won't take very long. actually, because a number of these are very short. But these are really good lessons to help reinforce what we've discussed this evening. When you do end up filling all of these up after viewing each one of these lessons, then and only then do you upload this completed document into Canvas. So by no means do this. Don't just fill in the first one and copy this all down like this. Oh, I got them all filled in. This is great. Boom, I'm going to turn this in. I'll get a quick 120 points. Yeah, you could do that, but I don't recommend that. They're here as an assignment for you to do as individual tasks. So be honest with yourself and put in the dates that are appropriate to when you actually complete any one of these, okay? Okay. And upload that. So that's plenty of things that you can do between now and Thursday. What else is on Canvas? What else is on Canvas that you can do between now and Thursday is also do your circuit builds. I have both F and G. So F and G are on here, and I highly, highly recommend that you build these. And there's 2 circuit builds, so there's only 2 selfies you're going to take. However, the circuit builds are pretty easy, but the labeling is very specific. So here you go. This is the same circuit, 2 resistor circuit that we built. However, I've labeled these points of interest. So instead of the 100 and 330, I put in a 220 and a 330. So when you go to build this, your R1 is 220, your R2 can stay as the 330. I've built this exactly the same way. Red power rail jumps to the first resistor with a jumper to the second resistor to the upper right-hand pin of your switch, lower left-hand pin of the switch goes to a jumper wire, and then to the LED, to another jumper wire to go back to the source. It is identical to, hey, I see a kitty cat in the frame, yay, furball, cool. So with a 5-volt source. And it's very important you make reference of these points for yourself in some way, shape, or form. I've chosen to do this with Post-its. And what I've done with my Post-its is something fairly simple. I can find, oh, there it is, my Post-its. What I've done with my Post-its is, so here's a Post-it. And let me go off of this for a moment, stop the share, just show you how I did mine. So here's a Post-it, here's the sticky edge of the Post-it, and I put this down, and I'm going to use a pen, and I'm going to write A, B, B, C, C, D, D. I'm going to write it like that. Then what I'm going to do is I'm going to get a pair of scissors, and I'm going to cut this way. And then I want an A. So if I want an A, cut out an A. So there's an A on my shears. I'm going to grab the A, and I'm going to paste the A on my circuit board. Boom. So there's point A. And so when I can do the same thing with point B, point C, point D. So with a 2 resistor circuit, my friends, it'll end up looking like this. This is the actual circuit that I built for circuit F. And what I happen to have on here is very specific. Here is, let me focus. And the schematic for this particular guy is right here. Let me raise this a little too close, sorry. There it is. My point A is from my power rail to the left side of my first resistor. Here's my power rail, positive rail, to the left side of the first resistor. On my schematic, it is a singular point. On my board, my point A is the red rail, or it could be this lead of the resistor. So there's 2 places where I can measure point A. They are electrically the same. Point B on my schematic is shown as a single point between R1 and R2. Well, because I'm using a jumper wire, I've got 2 points for point B. I'm going to jam this resistor back in because I stole it earlier. There's my 330. And the other side of the 330 is point C. Here's point C. It connects with point D in this corner. So that's the upper right-hand side of the switch. The other side of the switch is point E. So the lower left is point E. And point E connects to the LED. Well, point E is this side of the switch, this edge of the jumper wire, and this lead of the LED. So I can measure point E at 2 points. Same point on my schematic. On the circuit board, I have it spread out. And at the other side of the LED is point F, which connects to the negative side of the source. So here's the negative side of the resistor. That's labeled as F, and it does connect to the negative side of the source. So I have 2 labels for point F. So keeping track of this will help you with some additional exercises, which I will create between now and Thursday. But for the time being, you can get this built. For the time being, you can solve the VIR chart for this, and you can get circuit, that's F, you can get circuit G built. Here's circuit G. Here's the power supply that will go on the board. And circuit G is in your canvas. And circuit G is shown with this schematic, 3 resistors. And that's done with a 2 kilo, a 1 kilo, and a 5.1 kilo. So these resistors we have not used yet, but this is your circuit G. So this is a 3 resistor exercise. So that means your VIRP chart will have 4 rows instead of 3 rows. 2 kilo, 1 kilo, 5.1. All of this is in Canvas. So these are things that you can do between now and Thursday. Are there any questions for me before we sign off for this evening? Plenty of things for you to do between now and Thursday. But it's good we have a Thursday to follow up, because with Thursday, since we have an hour to up to 2 hours, up to you, first hour is mandatory, but the second hour is for any additional questions, and I'll stay for the second hour for free, free to you. And I'm sure there will be probably some follow-up questions. If you haven't thought of it by now, you certainly will think about it between now and Thursday. But any questions before we sign off for this?
Yeah, what time are we meeting? So I'm not late.
6.
Again.
Yep. We always start at 6. It'll go from 6 to 7. So that part is mandatory. And then anything after 7 is gravy. And I'm happy to share whatever time you need of me after 7 o'clock.
Okay. Sounds good.
Sounds great. Good. Any other questions? These are good questions. Okay, my friends, you have your marching orders. You know what's in front of you. Go forth and prosper. Try to get these circuits built, labeled, and at least measured for, and I'll create the charts by tomorrow. I'll have the fill-in sheets, the VIR fill-in sheets for circuit F and circuit G for you to fill in, but you can certainly build circuit F and then circuit G if you, there's room to actually build both on the board. So you can do this. If we take this power supply and scoosh it like all the way over to the edge, we can actually scoosh it that far to the edge, still make contact, have it overhang. That's okay. Notice if I put these both on the board, I easily have enough space to build both onto a single board. I happen to build them on 2 separate boards only because I happen to have a couple of boards, so I spread them out. Any questions? Okay, then we will sign off for now. I will hang tight for anybody afterwards, but the recording will stop